high above your head, far beyond the blue sky, the clouds, and even the air we breathe, lies an invisible force field. It's not made of metal or concrete. It doesn't shimmer or glow, but it's always there, surrounding you. It is the Earth's magnetic field, and it is our planet's first and last line of defense. Without it, the surface of the Earth would be bombarded by lethal radiation. Our atmosphere would slowly be stripped away by the solar wind. Life, as we know it, might never have evolved. And yet, for most of human history, we had no idea it even existed. In the 20th century, we finally began to understand the architecture of this shield. With the launch of space probes in the late 1950s, we discovered something astonishing. Enormous zones of trapped radiation surrounding our planet, the Van Allen belts. Invisible to the eye, but intensely dangerous to spacecraft and astronauts. But beyond the belts lies an even greater mystery: the full complexity of Earth's magnetosphere, a vast, ever-changing cocoon of magnetic energy that stretches far into space. This is the story of our planet's magnetic shield, how it works, how it protects us, and what could happen if it ever falters. To understand Earth's magnetic shield, we must begin not above, but below. Deep beneath your feet, some 3,000 kilometers beneath the surface, lies the Earth's outer core, a swirling ocean of molten iron and nickel. This metallic sea churns constantly, driven by convection, pressure, and the planet's rotation. As this electrically conductive liquid moves, it generates magnetic fields, in a process known as the geodynamo. These magnetic fields loop and merge, twist and stretch, forming a powerful global field that emerges near the poles and stretches into space. This magnetic field isn't static. It wobbles, flips, and pulses with time. But on the scale of decades to millennia, it provides Earth with a remarkably consistent dipole field, like a bar magnet with a north and south pole. It's this internal engine that creates the invisible magnetic shield we depend on. But the field doesn't stop at the surface. It stretches thousands of kilometers into space, forming a protective bubble, a magnetic force field known as the magnetosphere. In 1958, during the early days of the space race, the United States launched Explorer 1, its first successful satellite. Equipped with a simple Geiger counter, the satellite was meant to study cosmic rays. But what it found shocked scientists: intense zones of radiation encircling the planet. These belts, named after physicist James Van Allen, who led the mission, were the first concrete evidence that Earth's magnetic field traps and controls high-energy particles. There are two main Van Allen belts. The inner belt, stretching from about 1,000 to 12,000 kilometers above the surface, contains mostly protons. The outer belt, reaching from about 13,000 to 60,000 kilometers, is dominated by electrons. Together, they form donut-shaped rings of radiation, charged particles spiraling along magnetic field lines, bouncing between the poles, sometimes for weeks or months. These belts are both a triumph of planetary protection and a serious hazard for human exploration. Pass through them unshielded, as early Apollo astronauts did briefly, and you risk severe radiation exposure. Even today, spacecraft must be carefully designed to survive prolonged exposure in these zones. But where does all this radiation come from? Much of it originates from our own star, the Sun. The Sun constantly emits a stream of charged particles, known as the solar wind. This wind, made of electrons and protons, races through the solar system at speeds exceeding 1,000,000 kilometers per hour. When this supersonic flow hits Earth's magnetic field, it creates a dramatic interaction. The solar wind compresses the field on the day side, the side facing the sun, and stretches it into a long, trailing tail on the night side. This forms the magnetosphere, a teardrop-shaped region enveloping the Earth and deflecting most incoming solar particles. But during solar storms, or coronal mass ejections, the sun hurls vast clouds of plasma toward Earth. These events can overload the magnetosphere, injecting fresh particles into the Van Allen belts, supercharging them, and triggering geomagnetic storms. These storms can produce stunning auroras, the northern and southern lights, as particles funnel down magnetic field lines and collide with atoms in the upper atmosphere. But they can also disable satellites, disrupt GPS, and even knock out power grids on the ground. Earth's magnetic field is our shield, but it's constantly being tested. For spacecraft engineers, the Van Allen belts are a challenge that must be delicately managed. No modern satellite can simply camp out in the middle of these belts without robust shielding. Prolonged exposure to high-energy particles can fry electronics, corrupt data, and degrade solar panels. Even astronauts in low Earth orbit aboard the International Space Station remain safely below the most intense regions. When missions go beyond, like the Apollo missions to the Moon, flight paths are carefully planned to minimize time in the belts. The belts also vary over time. During intense solar activity, the outer belt can swell, split, or even form temporary third belts, as observed by NASA's Van Allen probes between 2012 and 2019. Sometimes, the belts thin out dramatically, only to be replenished within hours. It's a dynamic system, pulsing, breathing, responding to the sun's mood swings. Understanding the belts is essential not just for technology, but for the future of human spaceflight. As we venture farther, to the Moon, to Mars, and beyond, we must learn how to safely pass through this magnetic minefield. Earth's magnetic field isn't as stable as it seems. In fact, it drifts. The magnetic North Pole has moved thousands of kilometers over the past century, accelerating in recent decades. Compasses must be recalibrated, navigation systems updated. But even more profound are the field's reversals, full flips of the magnetic poles that occur every 200,000 to 300,000 years on average. The last full reversal happened 780,000 years ago, meaning we may be overdue. During these flips, the field weakens, sometimes to just 10% of its normal strength, and becomes chaotic, with multiple poles appearing and vanishing over centuries. What would happen if a reversal began today? The Van Allen belts would likely become distorted or disrupted. More solar radiation might reach the atmosphere, potentially affecting satellites, communications, and climate systems. But we wouldn't be left defenseless, not entirely. Even a weakened field would still provide partial shielding. Still, it would mark a dramatic shift in the space environment around Earth. A reminder that even our planet's most fundamental systems are in motion. The Van Allen belts are just the inner skeleton of a much larger structure, the magnetosphere. This sprawling region extends nearly 60,000 kilometers toward the sun and millions of kilometers into space on the night side. It's shaped by an ongoing battle between Earth's magnetic field and the solar wind. Instruments aboard satellites like Themis, Cluster, and MMS, Magnetospheric Multiscale Mission, have revealed the magnetosphere's stunning complexity. Magnetic reconnection events, where field lines snap and reform, releasing bursts of energy. Plasma bubbles and substorms that ripple through space. A constantly shifting boundary, the magnetopause, that expands and contracts with solar activity. In many ways, The magnetosphere is like Earth's invisible weather system, with storms, currents, and turbulence that play out on scales far beyond our sight. It's also the birthplace of auroras, where particles spiral down field lines, collide with oxygen and nitrogen, and ignite the skies with eerie green and red lights. For all its invisibility, the magnetosphere is a dynamic, living extension of our planet.